We now move into writing Verilog code to describe simple storage elements such as D latches and D flip-flops. So I'll go through some codes that describe a latch, and then I'll move and show you how to write code for D flip-flops and activated by different edges of the clock. But before I get started, I just want to mention that we can definitely go ahead and figure out how is the D flip-flop or D latches actually constructed with NOR gates, and just use data flow modeling or even gate level modeling to actually construct these latches and flip-flops, and use hierarchical design like we did when we talked about latches and flip-flops. However, what I want to do here is I want to show you how to use behavioral modeling to describe these storage elements, because in my opinion, they're the most useful or most used modeling style when we deal with sequential circuits. You will see behavioral modeling used heavily with sequential circuits. So let's get started. First, I'm going to talk about D latches. Okay, so we're starting with this particular latch. It's actually a D latch, okay? And this particular D latch, I went ahead and I created the module and I created the inputs and outputs. It takes, as the diagram shows me, it takes an input D and it takes an input clock, and it gives me a couple of output Q and Q bar. Sometimes it's Q underscore N for a negative or something like this, but we're just going to call it Q bar, okay? So now how do we write this particular latch? Well, again, we're doing it behaviorally, so this is how we're going to do it. So first of all, we're going to open an always block, and the always block will should be activated whenever the inputs change. And the inputs are either D or clock. Okay, so this is how we want. So what we need is the following. We need it to do the following. If clock is positive, because remember it's gated as a D latch, okay, Q should be equal to D. And else I want Q to be equal to itself. Nothing should change, okay? And again, we're including this else in here because we do not want, well, actually we can actually exclude it because we are building a latch. But if we did not want a latch because we were building combination of circuits, we should have used the else. But anyway, it's because out of a good habit and out of a style, I usually could include it anyway, even though it seems to be meaningless. And just for the sake of completion, I will always use the following as well, which is Q equals Q. Nothing changes, basically. That's what I'm saying. Okay. All right, so let's do this here. So we save it. Of course, it's complaining because this should be actually a register because we're assigning it within an always statement. Okay, and now next what we need to do is we need to figure out what to do with the Q bar, and the Q bar is pretty straightforward. It's actually just the opposite of Q. That's how it should be. So we can say Q bar should be not Q, and that's it. We're done with that. Now, if we actually open the elaborate design just to make sure that the D latch is actually the top file, so we open this elaborate design in here just to see what we will get. I'm hoping that we will get an RTL latch, and RTL stands for register transfer level, and that's the type of code we're writing. It's actually just Verilog code. And that's exactly what we got. We got an RTL latch. It takes a D input and a clock, and it gives me a couple of input outputs Q and Q bar, and you saw how we got Q bar. Okay. So Q bar is, generally speaking, sometimes it's included in these storage elements, others is not. I just wanted to show you how you can generate it, but from now on in the rest of this module, I probably would not include it unless it's necessary. Again, I could have just written this code without these Qs, and you should actually, the Vivado will infer a latch, and that's what we're looking for, but for the sake of completion and good coding style, I'm just gonna keep it. Alright, so now we move into writing code for a D flip-flop, and let's pick up this particular D flip-flop, okay? And this particular D flip-flop tells me that it's activated by a negative edge of the clock, so let's see how we can actually write this. So I went ahead and I created that module, and I call it D flip-flop negative for negative edge of the clock, or the falling edge of the clock. I'm taking a D as an input, clock as an input, and just Q as an output. You can include Q bar if you want to, but for now we're just not going to. All right, so the way we write it is the following. We're going to describe it behaviorally again. So we're going to start by saying always. And now this is where the difference is. Okay, I'm going to just do this here, and I'm going to say begin and an end. So the difference is the following. This particular output here, Q, should only be activated whenever the negative edge of the clock appears, or the falling edge of the clock. And the way we actually write it is this way. So we say neg edge of clock. And that's the only time when I want this particular flip-flop to be activated. And at this particular moment, I don't care what the value of clock is. I know it got activated. That means I am at a negative edge. I just need to be Q to be equal to D. And that's about it. This is how a flip-flop is inferred. So if you actually go and just to make sure that we get exactly what we're expecting, we're going to make that D flip-flop as my top file, and then we're going to create that schematic just to see it. Well, of course, it complained because this should be a reg. Okay, so we're going to do that one more time. We'll save it, and we're going to do schematics in here. And we did get something called an RTL reg. It's actually a register is a type of, like a register is another word, as you will see, or as you know, which means like a bunch of flip-flops. In this particular case, it's just a single flip-flop, and that's what we got. And we got the negative edge of the clock, as you can see in here, and that's a D flip-flop. Okay, so now we move on to writing something similar, which is just activated by the positive edge of the clock, and we can easily do it this way. So we're going to go in here. I created another file. Let me just zoom out here. So I created something similar. It's actually the same thing. It's just, let me show you. So we're going to do always, and it's instead of negative edge of the clock, you can say pause edge, okay, of the clock, and then here you can say begin and end, begin and an end, and you can say, well, I want Q to be equal to D, and you're going to get a positive edge triggered here. And of course, it's going to complain because this is assigned within an always. It has to be of type register. And now it'd be interesting to see the differences between the three devices. So a test circuit would be this one here. So I went ahead and I created it already. And all it does, it actually compares the storage elements. It takes the single input D, like the one you see in here. Okay, and it takes, of course, a clock as well as an input. So this is the clock. And what I did is I have three output. One is here, QA and QB and QC. And what I'm showing you in here is a latch, a flip-flop activated by the positive edge of the clock, and a flip-flop activated by the negative edge of the clock. And I just went and instantiated one instance of each, and I just connected them to the appropriate signals. And now I have a test circuit. So the way we're going to see it is by developing a test bench. And writing test benches at this point is probably straightforward. However, I just want to show you something a little bit new here, and I think it's worth your time. So I'm going to go ahead and just go and say, okay, I have a new test bench. I have created a test bench, not a complete one. What I did is I went and I created the signals that we needed. It's actually the clock and the D as the input. And instead of QA, QB, QC, so in the output, I get some signals that I know what they represent. I call them Q latch, Q FF positive, Q FF negative. And I connected them to the A and B and C so that on the output, the final output, we can figure out which one is outputting what. Now, generating the stimuli is what's probably worth your time in here. So let me show you. So first of all, we need, in sequential circuits, we need a clock. So generating a clock, there is multiple ways to do it, but I think it's the easiest way to do it is the following. So what we're going to do is we're going to define something we call a local parameter, and a local parameter is a parameter like the parameters we've been dealing with. It's just not exposed outside a module. So if you're writing a module, usually you write the parameters next to the inputs and outputs and local parameters inside. You can use parameters, there's no difference, but just so that you know if you've seen it. So I'm going to say T equals 20, and that particular value will be my clock period, the period of the clock. So I'm going to say period clock, okay, or clock period. Let me just do that here. Okay, that's the clock period. I'm just going to parameterize it so that I can change it if I wanted to. If I want to change the frequency of that particular clock. Okay. Now, how do I generate it? Well, I'm going to have to do an always. And I want this always to always run, so I'm not going to give it any sensitivity list. So this will run forever. As long as the simulation is running, it will run. And what I will be doing is I'm going to say, okay, clock at the very beginning has to be 0. And then what I'm going to do is I'm going to wait, but instead of just giving it a specific number, which is for half a period or something, which is 10, what I'm going to do is I'm going to say T divided by 2. Okay, and then I'm going to say clock should be 1. And then I'm going to make it wait for another half a period. Okay, so making it with a local parameter this way allows me to change the clock period on the fly. So if I wanted a different clock period, for example 10, now I have a clock that I have generated a clock with 10 nanoseconds or so. And of course nanosecond is because the time scale is it's actually 1 nanosecond in here. Okay, so now we're going to keep this here at 20. So this is 20 nanoseconds, and that's how a clock actually is generated. So if I actually went ahead and I just ran the simulation, you probably will not see anything in the output because I didn't generate any D's, any input, but you will definitely see the clock. So let's see that. Okay, so there you go. So we have that in here. Of course, the D and the outputs are unknowns because I didn't generate any D's, but what's interesting is what we have in here, which is the clock. Let me zoom a little bit in here. So, or let me just zoom from the very beginning. It's probably easier to see. And you can see this is actually 20 nanosecond, 40 nanosecond, 60 nanoseconds. It's exactly how I described it. All right, so let's go ahead and generate the actual stimuli for D. And I'm also going to show you something a little bit new. And these are basically some timing control structures. I have showed you one already. So now we're going to move to showing you a lot more, or a little bit more. So we can use an always because it runs forever, or we can use initial. Initial just run one time. Okay, it's similar to always. It just runs whatever the code is in it. It just runs once and that's it. It stops. This one here would run forever. Okay, so in an initial, what I will do is I'll say, okay, let's say D initially I want it to be 1. And then before, what we did is we said, okay, let's wait for 20 nanoseconds or whatnot, and then we can change it to whatever value we want. But now we can, as it turns out, we can actually use that T in here that we defined. So we can say, okay, let's wait for 2 of the T, basically 2 clock periods, okay, 2T. And then we're going to change D to be, let's say, 0. Okay, so now we're going to wait for 2T, which is 40. So you're going to see after 40 nanoseconds, and once you can pause the video and see it, or run the test bench and see it, you're going to see that. So these timing constructs in here are visible right in front of you here. So the first one is the one we saw. This one is the one that I just included. So let me show you this particular one in here. So this particular one, because I have a clock now, I can actually use those positive edge and negative edge. So I can say, well, wait for the positive edge of the clock. So now here what I'm going to do is I'm going to say wait and then do nothing. So I'm going to use the semicolon. If you don't use it, it'll not work as expected or as I wanted. So what I'm doing in here is I can give it how many seconds I want. I'll change it to 0, and then I'm going to tell it, hey, wait for the next positive edge of the clock, no matter how far this is. It could be 2 nanosecond, 1 nanosecond, maybe 20 nanosecond. I don't know. I just care about a positive edge of the clock. At that particular moment, what I want you to do is I want you to change D to be 1 bit 1. Okay? And that's how we can do that. So that's the next one. You can do this for positive edge or negative edge. It doesn't matter. You can use clock or actually reset any signal you wish. If you wanted something that is going from 1 to 0 or 0 to 1, you can do that. And now here, what I want to do is I want to use these old school one, which is let's wait for 2 nanosecond. I'm doing this on purpose so that I'm changing it within a clock period just to show you how the latch is actually changing with the D without it. Remember, we're still testing latches and flip-flops, okay? And then here, we're going to do this, and then here we're going to wait for 4 nanosecond D equals 1B0. And now what we can do is this one in here. Let me show you that guy here. So this guy, we can repeat something. So for example, I don't want a single positive edge. What I want is, let's say, repeat for 2 times. I want you to wait for 2 negative edge of the clock. And of course, I'm going to have to use that semicolon. So this particular construction or structure, it tells me, okay, do a couple of negative edge of the clock and then do the following. And that following is actually change D to be 1, okay? And that's how we can do this. Of course, wait, we don't, like, it's not applicable to this particular example, but you can see it later. If you want a certain input, maybe switches or something like this, or whatever it is that you're generating. We don't have switches and test benches, but you can wait for a specific value, or you can wait for certain signal to be asserted. Y could be just a single bit. And lastly, stop, which we have used it with an always before, but I just want to tell you that you can also use it within here. So for example, you can tell it to wait for 20 nanosecond and then stop the simulation altogether. And then you can pause this one here and you can run the simulation and you'll see exactly this, whatever I wrote in here, you're going to see it. So let's, hopefully it will work. Let's see it. All right, so we have that, and hopefully it is exactly what we expect. So I'm going to just open this and put it at the very bottom in here. And we have, we start with D equals 1, and then we started like, hey, we'll wait for 2 times 2, 20, which is 40. So I'm hoping at the 40 something changed, and yes, it did change in here at D. And then what we said is like the positive edge of the clock. Well, this is the next positive edge of the clock. That's exactly what happens. We set D to be 1, then we waited for 2 nanoseconds. That should be 52. That's correct. That's at 0. And then we wait for 3 nanoseconds. That's 55. And then we wait for 4 nanoseconds. That's basically here. And then we wait for 2 negative edge of the clock. So this is 1 and this is 2. And that's actually when we change the D to a 1. And then we wait for 20 nanoseconds, which is after the 80, it's the 100. And that's basically when we end the simulation. This is exactly what I expected. So now because we were testing latches and flip-flops, so in here you can see now you probably know why I named these signals a little bit differently. So I know that this is a latch. So that tells me whenever the clock is positive, it's actually changing accordingly. And you can see that specifically here, actually. You can see that in here. So you can see that D is changing and Q latch is changing because the clock is in the positive. When the clock is negative, it doesn't do that. And you can see with the positive edge of the clock, I'm expecting this here to change, and this one here to change, and this one here actually to change, and so forth. You can actually read it. And the negative edge of the clock is this one here, which is the falling edge.